So let's get this session started. And it's my pleasure to host this session and introduce Gael Varoquaux. I hope I said it well. Gael holds a PhD in quantum physics, but while doing his PhD, he also got interested in software development, and he started contributing to open source projects, first for data visualization, but that kind of, I guess, contributed to his interest for computer science in general and machine learning. He's now a research director of a group from Inria called SODA, and his current interests are on machine learning applied to public health, so using databases of health information, which are particular because sometimes maybe have issues like missing data, for example, and they are not crafted data sets like the ones that we typically use for our problems. So this is more real-world data. Also machine learning for mental health and democratization of machine learning. So as I said, he has been working on problems which address how to use real-world data sets. But also he has been contributing to tools. I mentioned before this visualization, but I guess most importantly, you were part of the foundation of SciPy, which is a library that I guess everyone here is using and basically changed the way we do machine learning with Python. And I think that one of the things that there are in common with all of these points is to keep an eye always on these real-world problems and real-world sort of evaluation also of the machine learning techniques. And that's one of the things, I guess, that you're going to talk today. So thank you, and all yours.
Thank you very much. I was actually more involved with scikit-learn than SciPy. I was involved with SciPy. No, that's fine. I was involved with SciPy, but I co-founded and I'm still leading the development of scikit-learn, which is a really interesting experience, teaching me a lot. Anyhow, today I would like to talk about model evaluation. It's something I've gotten worried more and more about in the last few years. I think it's really a crucial bottleneck for machine learning. And I want to drive the point that I really think it is the Achilles heel of what we do in research, in R&D, sometimes in practice. And with regard to academic research, I think there's something important, is that machine learning grew out of math and computer science, but it has become an empirical science, whether we like it or not, by the way. And I studied as a physicist, especially experimental physics. And sometimes I feel that my students that come out of math and computer science do not have the background of empirical sciences. And so I think as a community, we're struggling a bit with the fact that the way we gather evidence has changed. And I feel this a lot when I review papers. I've been reviewing for iClear, AI stats, triple AI the last few weeks, and I just think the quality of the empirical evidence isn't there. And I want to showcase a few recent adventures I've personally had. A few years ago, we organized a challenge to do diagnostic of mental health from brain imaging. So it's a topic I've been working on for more than 10 years. And so we organized a Kaggle-style challenge where the participants were given brain images. And the challenge was to predict or not the autism status. And there was a reasonable money incentive. There was $10,000 involved. I think the leading prediction would get 5,000 euros. So that's quite interesting. And what you can see, I mean, it was a really interesting thing to organize. But what you can see is that there's a bunch of people who brutally overfitted the public set. You can see the numbers, right? They're way out. Even though this was a setting where the incentives were clearly not to overfit the public set, right? And it's really human overfit. If we have access to all the traces, so we can look at what people did, and just people improved their scores, and after a while they just kept improving, but improving only on the public set, not on the private set. So it's basically human overfitting, right? It's not due to the algorithm, it's due to the analyst just playing with the thing. At the end of the day, the best performers were really very simple models. There were linear models, there was a graph structure, a graph of brain connectivity in there. People used graph neural networks, but they've been published to do fantastically well on this kind of data. They didn't work well. So really, we organized this challenge, and the conclusion of the challenge is that, well, linear models are what won the challenge. I'm not surprised, personally, as an expert in this, but I think it was the only way for us to drive this message. So with a friend and colleague, Varoquaux, we looked at, basically we had a feeling of failure of working for 10 years in machine learning to try to improve medical imaging and not really seeing the success that we wanted to see. So we tried to analyze the failure. We wrote a preprint that was called How I Failed Machine Learning for Medical Imaging. That was successful. The final published paper doesn't have this provocative title. And we go over many things in this preprint. But one thing that we did was that we looked at the Kaggle competitions that were done on medical imaging. And we looked at the difference between the public and the private set. The public and the private leaderboard, not set. So people don't have access to labels on this. They just have access to the score. And we looked at this, so it's the blue distribution that I'm showing. So it's kind of, the width of the evaluation error, because if I give you two different test sets, that's the difference between those two different test sets. And then the brownish bar is the gap between the winner of the challenge and the algorithm or the submission that was 10% further away. So what you can see is that in a few of those data sets, in a few of those challenges, the gap between the winner and the 10% best is actually smaller than the evaluation error. Because I've picked two different test sets, and I have a difference between the observed performance that is bigger than actually the improvement that made the gap. In the third, what we have is that on the private leaderboard, people perform actually significantly less well than the public leaderboard. So that's just human overfit. And out of those, we have one where we have an evaluation noise that is significantly smaller than the improvement gap. So one where we see an actual improvement. So what we see here is that we have a bunch of situations where we're just in diminishing returns. We're just optimizing things that are noise. And that is on a Kaggle competition where there's not really a strong incentive to do this. Now, I worry a lot about the publications, right? Where the incentive is to show the biggest number. And so if we look at publications over time on a specific problem, which is Alzheimer's disease diagnostic, and here really the most interesting question is the black line, the difference between progressive mild cognitive impairment and, I don't remember what the S stands for. Well, SMCI. Stable, I guess. And what we see is that across time there is little to no progress. What we also see is that when people work on larger cohorts, they tend to get smaller prediction scores. One explanation is that those larger cohorts are more heterogeneous, but they're closer to real-life settings. Real life is heterogeneous. So we're not seeing strong evidence of progress. And finally, something that's more conceptual, I don't have a graph for this, is that beyond those numbers that we're looking at, those progress do not reach the clinic. And that's something that's fairly well known by clinical researchers, especially biostatisticians. that, you know, machine learning people publish beautiful benchmarks, but it never works in real life. And we machine learners, by now, do not have at all the trust of biostatisticians. When I work with biostatisticians and I tell them I'm a machine learner, immediate mistrust. And now I need to show them that I know statistics, I understand what they do and everything, but they don't trust me. And some of the failures are, for instance, that the algorithms used information that, for instance, was added by doctors on the patient, for instance, on the patient's skin, to predict whether the skin was a skin cancer or not. So it uses information that is not present at diagnostic time. It's a consequence of the diagnostic. Or it was trained on labels that were not really trustworthy because, you know, machine learning is data hungry, and we just used whatever we could get and in terms of labels, you know, hoping that this would capture information. It captures information, but it captures bias, and it captures too much bias, which kind of washes out the useful information. So it's. By the way, I must stress that I do believe that machine learning can bring something to the clinic. It's just that we're doing it wrong. Add to this, you know, the problems of incentives in academia, which make things way worse. We're in trouble. And finally, to beat a dead horse, I've started working on different kind of data sets. I've started working on patient electronic health records, and those are what we often call tabular data. So it's not signal processing at all. It's data of columns of different nature, age, sex, address, weight. And there's been a literature in deep learning that's picking up on this, and I find this fascinating. And so we started with a student to work on this literature. And so we picked up, you know, beautiful papers with beautiful benchmarks. We downloaded the implementation, fixed them so that they ran, and tried them out. And this went on and on and on. And we never could find that those algorithms were performing as well as the publication promised us. And those were serious, those were published in serious venues by serious labs. And so we eventually published not what we wanted to publish, but we published a benchmark that is basically a null result that is saying, hey, standard tree-based algorithms tend to work better than the latest publications in tabular deep learning. And we published this at NeurIPS. I'm quite happy that it went through. And so, you know, that's the kind of graph we have in it, where you see that as a function of time, you basically, the tree-based algorithms always have an edge over the deep learning algorithm. And I didn't want this to be true, by the way. We had started a PhD on tabular deep learning, so that's not what I wanted to be true. Okay, so we have a benchmarking problem. And, well, that can be a research topic. How do we do better benchmarking? And by better benchmarking, I want to say more valid benchmarking. There's this notion of validity, which has been developed a lot in social sciences, is much more than statistical validity. We're going to have a claim. This algorithm is better than this algorithm. Not the most exciting claim, but it's one that machine learning people like to have. How valid is it? In what settings is it valid? Is it statistically valid? Is it not statistically valid? Does it generalize to other setting or not? So for benchmarks to be valid, they need to reflect and to capture both the application setting, and that's something that we're seeing fails often, but also the ability to generalize. And so I'm going to give us maybe slightly mathy talk. I'm sorry, it's not a completely conceptual talk. And I'll explore, for instance, classification metrics. And I hope that you'll learn a few things about classification metrics, you know, that we think we all know well, but that are useful to think about. And I'll explore also how to quantify generalization error. And same thing, I hope that you'll learn a few things about, you know, train test splits and cross-validation, basics. Okay, so classification metrics. And the challenge here is that we want these metrics to really capture and reflect the application. And this is important because we machine learners tend to focus on these metrics. I don't think that's a really good thing, by the way, but it also drives we need to admit that it drives the field forward. When we get a metric that's a good one, and then we get thousands of machine learning researchers to optimize it, things happen. It has happened in natural language processing, it has happened in computer vision, so if we can get in this setting, we're closer to improving our applications. And I'm going to start with today I'm going to focus on the very simple setting of binary classification. So really the simplest setting. And the first, problem where we see metrics being challenging is when we have imbalanced classes, right? We have much more of one class than another class. And I'm sure I don't do the same applications than you, but I'm sure you have those problems. In this case, the accuracy is not very informative. So we like the accuracy, counting the number of errors, because it's a simple number that we can easily interpret. But it may not mean a lot if we have 90% of class 0, 90% of healthy individuals, for instance, because then only predicting class 0 gives me an accuracy of 90%. So, I can't really interpret the accuracy. So then what people do often is that they look at what's known as balanced accuracy, which is they separate counting the errors in class 0 and class 1. And the errors in class 0 can be called the sensitivity. It's the error in class 1, sensitivity, a fraction of class 1 that is retrieved. The errors on class 0 can be called the specificity. And then we can do the balanced accuracy as the average of the specificity and the sensitivity. So we're counting differently errors in class 1 and errors in class 0. And now I want to introduce a few notations. I will call the truth T. And when I have class 1 in the truth, I'll call this T plus. And when I have class 0, I'll call this T minus. And I will call the prediction P, P plus, and P minus. Specificity and sensitivity give me the probability of the prediction knowing the truth. Okay? But maybe in terms of application settings, what I'm really interested in is the probability of the truth given the prediction. And so here, it's another set of metrics that are known as the positive predictive value or the negative predictive value, and they can be related to the specificity and sensitivity just by Bayes' theorem. So it's super simple. It's basically, we need to account for the prior class probabilities. If I have imbalanced classes, one class is much more likely than another class. So when I do my Bayes formula, I have the ratio of classes that's known as the prevalence that appears. Okay? And so then we can define a new summary metric that some people call the markedness, that is pretty much the average of the positive predictive value and the negative predictive value. So the probability of the truth given the prediction. Now the drawback of this is that it depends on the prevalence. The same classifier, I will give it a data set with different prevalence, I'll get different PPV and PV, different markedness. So it's not something that is intrinsic to the classifier, it's related to the classifier and the data set. And now we can do things that have been known in medicine forever, which is we can look at odds. Medicine uses odds a lot, and so the odds of an event A is the ratio between the probability of A and 1 minus A. And this ratio has interesting properties. And so then we can look at what's defined as the likelihood ratio of the positive class, which is the odds of the truth given the prediction divided by the odds of the truth. And if we do the math, and it's fairly easy, and the math is done in this book chapter with Olivier Colliot that we wrote, but it's really easy. You can see that it doesn't depend on the prevalence. And that's something that's fairly general of odds ratio, is that odds ratio don't depend on prevalence. And this is one reason why public health uses odds ratio a lot. And the proof is also in the book chapter. But it's very well known. And so when we have this, we have the LR plus, the likelihood ratio of the positive class, and we can define the same for the negative class. And what we can see is that it's related to the probability of the truth given the prediction, or rather the odds of the truth given the prediction, but it's independent of the prevalence. So it only characterizes the classifier. And so we can use this to reason on the usefulness of a classifier across a set of different settings with different class prevalences. So for instance, I can use this to reason on the usefulness of a COVID test, but the prevalence of COVID keeps varying. So this actually literature was developed for diagnostic tests, not for classifiers. And so typically I think that the LR plus and LR minus should be used more often, and we've just added them to scikit-learn, and they're very classic in public health. What we really see here is that we need to extrapolate between test sets of different prevalences, because the prevalence might vary across time. Might vary both across time, but also in the populations that we look at. Okay, so now we can look at another thing that is very important, is how confident am I about a prediction? And this is related to the notion of calibration, which has become quite popular in the last few years. And so the question is, can we interpret a classifier score, so a continuous score from a classifier, as a probability? And so there's the notion of calibration, that is defined, we say that the classifier is calibrated if the average rate for the average error rate for all the samples with score S given by the classifier is S. So on average, all samples that are given a score S, on average, I have a fraction of error that is S. And so typically the way it's done is it's computed using Binson scores. So we take the score, we take all the samples that have the same predicted score, and we look at the empirical error rate. And it's related to things such as the expected calibration error, which really looks at average error on the bins of the score S. Now, an important thing is that this is an average error. This is not an individual error. And people stop there because it's easy to compute because you're binning on S, and S is a one-dimensional thing. It's the classifier output. But it certainly is not enough. Given that it's the average score, a classifier can be calibrated, assigning a score of 0.6 to individuals, but in all those individuals, we could have two subgroups, people who are blue and people who are orange. And those subgroups might have an error rate of 0%, so 100% success rate on one end, and 20% on the other end. And because it's the average error rate, the average of 100% and 20% is 60%. So this is a calibrated classifier. It's calibrated, but it's certainly not giving me a confidence score that is trustworthy at the individual level. So this problem is related to the notion of fairness, but it's also related to the fact that calibration in no way controls individual probabilities. And this is an error that is made in so many publications. Sometimes it's not made explicitly. Sometimes people write things with plain English and things get entangled. So we just put a preprint online on this topic. And so there is another set of metrics that control individual probabilities and that basically quantify whether the classifier approaches P of Y given X. And those are known as the proper scoring rules. It's a property. One example is the Brier score, which is basically the squared loss between the observed binary label and the predicted score. But it's the log loss is also a proper scoring rule, and the proper scoring rules have the property that they're minimal when the estimated score is equal to the probability of Y given X. It's a non-trivial property because we do not have this probability of Y given X, right? Where in an empirical setting, we don't have access to this property, but we know that they're minimal. Now, people don't seem to like them empirically, and I think there are two reasons behind this. One of them is that they can't be interpreted as an error rate. I give you a Brier score of 0.1, you don't know what it means. And relatedly, there's no scale. Now we can go further and we can decompose scoring rules into error rates, and this is a work that's been done a few years ago and that we're recycling. And for this I need to define a bit what objects we're using or manipulating. So I'm going to call S the output of the classifier, so it's a non-thresholded output, so it's a continuous value, and it's a random variable because it depends on X, which is also a random variable. I'm going to call the label probabilities the probability of Y given X, so it's basically the expected label, okay? And it's not the same thing as the label, because the label may have noise. The expected label is what I will find on average, on expectation. And then the calibrated score is defined as the expectation of the expected label given the classifier output. Okay? So it's knowing the classifier output, knowing that my classifier said S equals 0.6, what's the label probability? This is what calibration is looking at. If we write things well, this is what it's looking at. And now, a scoring rule, prior score, log loss, for instance, can be decomposed in a sum of calibration error, which is going to be the distance, the discrepancy between the classifier output and the calibrated score. Okay, so if a classifier is calibrated, this calibration error is 0. A grouping error, which is the discrepancy between the calibrated score and the individual label probabilities. And an irreducible error, which is what's left, basically the part of Y that I cannot predict because Y is not a deterministic function of X. Okay? So if I have those three terms, I have fully characterized my classifier. And technically, I need only the two of them. So calibration error, we know it's what everybody's been looking at. And what we did with Alex Pérez-Lebel and Marine Le Morvan is that we studied the grouping error or grouping loss. So here I'm plotting an oracle calibration plot. I'm plotting a plot where I'm showing the true probability as a function of the predicted confidence. Now, I can't plot this because I need to have access to the true probability, so I can do this on simulations. And what you see here is that we have a classifier that is calibrated. It has no calibration error because on average, the predicted confidence is equal to the true probability. But that's on average. Okay, it's averaging across all those data points. However, it has plenty of grouping error because the classifier is sometimes overconfident on some samples and sometimes underconfidence on other samples. If it were not, it would be just this plot would just be a straight line, okay? So really the grouping error measures, in a sense, the dispersion of the score. It's kind of the variance term in this calibration plot, whereas the calibration error is the bias term, okay? Now the problem is I can't do such a plot in real life because I need access to true probabilities, and this is where it's really difficult. And I think this is one reason why people have been focusing on calibration errors, that calibration errors are binned. They're expected errors, so they're much easier to compute. So I'm going to cut a long story short. The paper has a lot, but we contribute a way of estimating a grouping loss, the grouping loss. And the intuition is really, it's about estimating true probabilities on well-chosen bin. So if we can choose bins that capture a bit the inhomogeneity of predictions, and then the devil is in the details, in the math, is that we need to control the different errors that are due to binning, and we need to correct them. And that's where the math comes in. But as far as I know, this is the first estimator of grouping loss. And we hope it will push people to look more at grouping loss, because focusing only on calibration error is leaving massive blind spots in the evaluation of classifiers. Okay, so to summarize a bit this part, I took a very simple example of binary classification metrics. And I explored a few interesting aspects of them. The point being that when we do benchmarks, we need to think well about what the metrics that we're using measure. I think we should often be thinking in terms of the probability of the truth given the label and not the converse, which is easier to estimate. LR plus is interesting, but it's not the only thing to have in mind. And clearly, we need to be thinking more in terms of uncertainty. That's something that's very, very important to applications. Uncertainty in all kind of applications, self-driving car, health applications, you need individual uncertainty. And something that's well known to people who worry about benchmarks and metrics is that in no way a single number will ever tell the whole story. You will have structure in your error. You will have different kind of trade-offs. And when we organize a benchmark like a competition, we need to choose one error, which we're going to use to rank people, to rank submission. But in no way should we get the story here. Okay, now I want to move to a different part, which is how do we quantify generalization error? And this is some work I did a few years ago when I was on sabbatical at Mila in Canada. So, the way we work is we take our data in machine learning, we split it in a train set and a test set, and we're done, right? Easy. Well, first, we need to ask ourselves, what are we benchmarking? What's the question we're asking? And there are two different questions. One is, I'm benchmarking a prediction rule. So I'm given a rule that given data predicts labels. This rule may come from experts. It may not come from a machine. I'm going to put this rule in production. Other scenario, I'm benchmarking a training procedure. I'm given a procedure that outputs a prediction rule given training data. The first setting is typically for application claims. For medical applications, for instance. As an application scientist, I do not care how you obtain your rule. You may have done all kinds of horrible things. You may have guessed it because you're an expert in the field. If it predicts really well, if it's very reliable, if it's fair, I can use it. I can put it in production. I can do medical or public health decisions with it. Now, the second scenario is what machine learning research worries about. I'm doing a claim on an algorithm. Those are two different settings. And I'll show you that we need to think about those two different settings in different ways. I see those two settings most often conflated, and that leads to confusion. So first, let's consider benchmarking a prediction rule. It's actually easier. So there's this notion in medicine of external validation. So we're given a rule, and we need to validate it, and we would like this validation to be external in the sense that it should be some form of strong validation. We should bring in test data that's different enough from trained data. So clearly no repeated acquisition of the same individual in the train and the test set, but ideally we want to show some form of rather strong generalization to a new site, generalization to later in time, because if we don't do this, we're going to have a prediction rule that's brittle in real life. Now, the theory of machine learning is mostly on IID data, so that's not in the standard theory of machine learning. It's related to domain adaptation or things like this. But if I'm doing application, I don't care about the theory. I'm going to put this thing in production, and I want it to be robust. So I need to test it in a fairly stringent way. And another well-known problem of medical research is that my validation data, my test data, needs to be representative of my target population. That's something that's very common of all medical research. So did you know that the pulse oximeters that we use to measure the oxygen level in the blood that you put on fingers, they don't work really well on dark skins? Well, I guess there was no dark-skinned people in the test data. It happens more often than we think. And so the first thing that a medical researcher will do when reading a clinical study is look at the demographics of the study. And worry whether those demographics are representative or not of the target population. We need to do the same thing in machine learning. And you know, there are ways of doing this. We can match statistical moments. We can look at propensity score or re-weighting to minimize confounding associations. It's a statistical problem. We can worry about it. We just need to keep it in mind. Okay. Once we have this, we still have a problem. Our test set is limited. And the quality of our evaluation will be limited by the number of test samples. We never think about this. We always want more training data, but our test data are also limiting. And so, for instance, this is sampling noise under a binomial distribution for a test sample of 1,000 data points. Now, in medical imaging, 1,000 data points is huge. But from what I saw in the posters, 1,000 data points is also quite related to what you have in your field. Look at the binomial distribution. It's wide, and that's under the best settings. You know, those data points are IID. So that's intrinsic sampling noise. We can't do better than that. Okay? It's because we have a general population that we do not have access to, and we've sampled 1,000 data points from this. And so if we were to sample another 1,000 data points, we would have another measure. It's sampling noise. And as we've seen, sampling noise is not negligible. And this is on Kaggle competitions, but with Xavier Boutillier, we looked at computer vision and NLP, and we showed that sampling noise was not negligible in current deep learning research in computer vision and NLP. And I almost wonder whether the way research progresses is not by people building better, larger data sets. And it's not only about larger, it's also about better curated labels. And then this helps pushing the boundary of algorithms further. Typically, I find that in computer vision, we don't give enough credit to ImageNet, which was a paper which really pushed forward the field by enabling development of better algorithms. So it's useful to think about uncertainty due to the final test sets. So to know when to stop, what to trust when you're reviewing papers, when you're doing your own research. My experience doing data science is that it's really important to know when to stop. If I work too long on a problem, I will overfit it. So I just need to stop at some point. It's also important to stop because we just keep building more and more complex pipelines. Those pipelines are fun on our computer, but they just cannot be deployed to any real-life setting. So one really easy thing to have in mind is binomial confidence intervals. Now, they're a fairly simplistic model, but the nice thing is that we can just compute them really easily. And to make things even more easy, in our book chapter with Olivier Colliot, we're given this table of binomial confidence intervals. And they can be useful just to, as a rule of thumb of the kind of error bars that you have on your performance metric. I keep referring to these things. So I hope you'll find them useful. The book chapter is available on my webpage in the preprints. Okay, so we've just seen the simple setting, which is benchmarking a prediction rule. We've just been worrying only about the uncertainty due to the test set. Now, if we're going to benchmark a learning procedure, more is going to creep in. So the setting is that we're given a procedure that outputs a prediction rule from training data. So technically, this prediction rule is actually, if we want to do a theory, it's actually a random variate because it's a function of the training data. Okay? And this is the setting we are when we want to do machine learning research claims, which is most often what we do in the kind of research that we do. So I want to say, I've contributed to the novel Prunkl method, and it improves prediction by 0.01%. And I want to publish this. And those things come with an incredible number of arbitrary components. And we can tweak them. For instance, we can tweak the random seed. And there's this fun paper that shows you that if you tweak the random seed enough, you'll get excellent prediction performance. And the example is on computer vision. Of course, this is an ironical paper because it's absolutely useless to tune a random seed. Why is it useless? Because it will not carry over to new data. My super magic random seed is not a property of my algorithm. It's just something I've tuned. And I do run the risk of overfitting my test set when I do this, by the way. Well, it's not about having a debate of whether tuning the random seed is good or bad. If your test set is large enough and your algorithm has terrible local minima, it may be useful to try a few random seeds and to pick the best one. The thing is, when you've done this, you've characterized the resulting prediction rule. You have not characterized the training procedure. Two different things. So with Xavier Boutillier, well, Xavier Boutillier did the hard work. He benchmarked different sources of arbitrary variance over a bunch of different classic computer vision and NLP tasks. And this was very resource intensive. He ran a lot of experiments on the Miller cluster, and he just, reran the evaluations, modifying arbitrary elements, such as the data augmentation, the order of the data, the weight inits, the dropout, numerical noise, which is just things we don't explain. We just rerun the same things, and things are different. And so I'm showing here, the impact that modifying these things has on the benchmarking result. And this is a relative scale. But these are internal components of the algorithms. We also have the split between the train and the test set, which is completely arbitrary. And so now if we start, doing different splits between train and test set, which is what we called here bootstrap. Technically, it's not a bootstrap, but what we see is that we observe a variance that is larger than all the others. And so until recently, deep learning research only sampled this, the weight in it. So only a small fraction of the total variance. So, and that's the best case. Quite often, there was a single weight in it. So it was massively underestimating the variance of the benchmark. So better evaluation is simply to sample all these choices multiple times, including the data split. And we've just reinvented cross-validation, which used to be cool 15 years ago. So I hear everybody say, I don't want to do cross-validation. It's too computationally expensive. I don't buy this. We're running incredibly expensive algorithms, but we're not willing to evaluate them well. This is just like saying, I'm not going to do a randomized controlled trial of brain surgery because brain surgery is dangerous. So I'm not going to, try brain surgery on people. Well, we're going to put it in production. So if we're going to put it in production, we need to evaluate it. Thank you. There's one last thing. Hyperparameter selection. Myself and quite a few others have become convinced that people routinely tune better the hyperparameters of their favorite models compared to the baselines. And that's not reported in the benchmark, because the benchmark just tells you, using this set of magical hyperparameters, I get this performance. But once again, if we're interested in a learning procedure, not a prediction rule, that's part of the learning procedure. Tuning hyperparameters is part of the learning procedures. Some learning procedures have hyperparameters that are much harder to tune than others. So if we're going to want to compare things, we need to compare things in taking into account the tuning of hyperparameters. Now, one challenge is that it's often done by graduate student descent, so basically experts that turn knobs, and that's hard to quantify. We could bootstrap students, but my students don't like that. So I really think we need to do more automated hyperparameter selection. And one thing that I'd like to push forward is random search. Now, random search is not super exciting. It's, picking randomly hyperparameters in reasonable distributions. It has a few benefits. One is that it samples all the hyperparameters in a homogeneous way, which means that if you have one that is not important, it doesn't waste computing power on it, which was the original motivation. I'm interested in it because then we can draw subsets of those random data points to estimate the variance. The nice thing about random search is that every point is statistically equivalent to the other. So I can mimic multiple random searches of smaller size by subsampling my random search. And this is what we did in the paper on tabular deep learning, and I suspect it's one of the reasons why we got different conclusions than what people had in the literature. They didn't really dedicate the same computing power to tuning their algorithms than the others. So I really think this should be standard. It's expensive. Well, that's what we're choosing to do. We're choosing to do deep learning. That's expensive. Okay, so if we want to benchmark training procedures, for instance, to compare them, we want to control arbitrary fluctuations because we want to know whether the difference between our training procedures are due to arbitrary fluctuations. And the way we can do this is actually extremely simple. We're going to sample all the sources of arbitrary fluctuations. We're going to sample data sampling, so the train test split, randomly sample training tests. We're going to sample all the arbitrary choices, the seeds, all the things that we have no really theory to set. And we're going to sample hyperparameters, which is hyperparameter optimization via random search. If we do this way, we're going to explore all the sources of variance, and we're going to be able to have fair comparisons between algorithms. Now, how do we account for the resulting variance? And it gets a bit complicated, and I'm running out of time. And there's one challenge, is that doing null hypothesis testing is difficult because we don't have independent data points. So we cannot do something like a classic statistical test, such as a t-test, a Wilcoxon test, across multiple folds. They're not independent. We cannot compute a standard error. We cannot divide the standard deviation by the number of fold. But we can do something different, which is we can use what's known as a Neiman-Person-like approach of statistical testing, which is we can test whether the probability of algorithm 1 outperforming algorithm 2 is bigger than a certain threshold. And to do this, it's just a question of counting how many times in our many different draws algorithm 1 outperformed our algorithm 2. It's not more complicated than this. At the end of the day, we don't get a p-value, and we could talk about this for a long time, but I claim we're not interested in a p-value. We're interested in a pragmatic point, which is maybe, algorithm 1 outperforms algorithm 2 by a tiny fraction, 51% of the time. That might not be very pragmatically interesting if it's 10 times more expensive. So we need to report those things. And if we don't have the compute power to do many samples, we can do a Gaussian approximation, and we do a Gaussian approximation. It's just a question of comparing the differences, the observed differences between the two algorithms to the standard deviations. It's really simple. People are often doing this. Sometimes people are reporting standard errors, which is standard deviation divided by the number of draws. This we shouldn't do because the draws are not independent. Okay, I'll conclude there. We need to think about our benchmarks. We need to think about the performance metrics that we're using, and they need to be suited to the application setting. Machine learning does metric chasing, which is both good and bad. If we choose good metrics, we can get people to improve them. And I think we need to think about probabilities. Probability of the true label given the predicted label, probability of the label given the input. And in the evaluation procedures, we need to account for variance. We really need to. We can't just look at point estimates. It's not that hard, and we need to make the difference between applying prediction rules and learning those prediction rules. Why do we need to do all this? Because our goal is to give procedures that generalize, and that generalize to our application settings. And for this, we may need to account for the mismatch between the data we have and the data that reflects our application setting. Thank you.
Okay, thanks, Gael, for the talk. So now time for some questions. Who wants to start? Okay, there's someone in the back.
Thank you for your talk, very interesting. I have two questions. One is about, do you have a formal definition of what you call empirical science? And my second question is, it seems that you kind of agree on the fact that we need to define collectively one metric for a task, and looking at how the metric evolves through different algorithms in more formal statistical ways. But do you think this is the end of the story, or do you think it's just a compromise? Because in many ways, I think that solutions can only be considered as a composition or a compromise between a lot of different objectives.
So in terms of what I call an empirical science, math, especially pure math, is a purely formal science. You start from a set of assumptions and you go from these assumptions to a conclusion. As long as the logical chain between those things is correct, your answer is correct. It's mathematically correct. Computer science, theoretical computer science, sorting algorithms, same thing. Some of the results in machine learning are like this. Make a set of assumptions on the data generating process, draw conclusions. But that's not the whole story about machine learning. We can play this game, and some people play this game beautifully, and it's very useful. But machine learning does not stop there, and what we've seen in the last 10 years is that we've seen progress that were pushed by observations related to experiments that were not driven by assumptions, and then the assumptions coming after. So this is what I call an empirical science. It's not only an empirical science, but it's also an empirical science. Now, with regard to whether choosing one metric is the end of the story, clearly not. I think it may be useful. I think also, even when we choose one metric, we shouldn't hide the others. We should choose one metric because it's a game and because games work. But we should certainly not stop there. And in this sense, over the years, I've become more and more aware of the fact that what we do in machine learning is put in production, and this has consequences on people, and it's not about the metric, it's about what this does to the people that we should worry about.
Another question?
Thank you very much for the talk. So you mentioned very correctly that one number is definitely not enough to summarize your results, right? And sadly, we see that probably too often in papers that all the results are summarized with one number. Then on the other hand, what do you think is the value maybe of having a more like exhaustive representation of your results, like let's say like a graph showing ground truth versus estimate, like a scatter plot where you have like completely exhaustive picture of the results of a method on a data set. I've seen that in some community. This is starting to appear rather than having like say the average error. You have like actually the whole graph, but then it's also more complicated to read. It's a bit more difficult to compare methods, but at least you have the full picture, right? So what's your take on this?
So when the data is a bit complex, you cannot represent the full picture. It's impossible. However, where you're getting at is something I learned when I was working with biologists, is that biologists are especially good at this, is that when you have very complicated experimental results or empirical results, you need to find what's interesting in there, and that's difficult because you have a problem that has many, many different facets. And then you need to convey it to the reader. And that's an art. And I think it's an art that is undervalued in machine learning, but is actually has a huge impact. There are a bunch of papers that are very famous that basically did this, that basically ran experiments and then conveyed what they learned from the experiment in the paper. That's something difficult, and it's something we need to learn more.
Thanks.
Okay. I think the first arm was the one over there. Yeah.
So I have a question about your opinion on one subject. So there's sometimes difficulty to find a proper metric. For example, when you have a generative model. I mean exactly, for example, when you have a denoising system. In audio denoising system, there have different metrics, and they are poorly correlate with what actually think it's a good quality. And after all, some guys came up with the solution that, okay, so we first train a model that imitate the human perceivance of audio of such denoise signals, and then they train the model and used it as a metric. What's your opinion on that approach? If the metric is properly done, is it okay, or is it too complex just to do so?
So there are two things that can give us difficulties. One is when we want to do claims, inferences, conclusions on unobserved data. Here, I'm assuming I have a set of observed label, whatever they are, and I can compare my output to observed label. If I don't have this set, if it's latent in some way, it becomes difficult. Now, I have a philosophical point of view that those problems are much more difficult and that we should, when we can, avoid them. But that's a whole different talk. Now, the question you were asking is, sometimes my evaluation metric is intrinsically qualitative, intrinsically related to human perception. Or, for instance, in the problems I'm interested in, health. Health is something that's quite difficult to define. It implies all kinds of trade-offs. What I prefer to do is to have long-term consequences of health, for instance, that are reasonably observable and what's known as ecologically valid. So if you look at denoising, for instance, maybe you have an end task at the end. And the end task may be, understanding, it may be recognizing songs, things like this. And of course, ideally you would like a human subject to understand. And so you're going to have to do some human labeling, but you can probably proxy it. So you can have a mix of proxy. But to me, the most important thing is that you want some form of ecological validity of your metric. And the research in social science and in psychology has looked at that massively under the name of the validity of measurements.
Okay, I think we have time for 3 more questions, maybe. So there's one over here. There used to be more before. Okay, sorry, I didn't see it. So. Yeah, let's start with this one.
Yeah, thank you so much for this enlightening talk. So as a kind of leader or one of the leaders of the scikit-learn, do you think kind of including those kind of form of educational content in the documentation, which is such an invaluable resource, or even kind of enforcing the good practices as a kind of default ways of benchmarking models in there, is the way to go, or is it kind of up to raising like general awareness in the field because it's so different between different applications?
So yes, I would absolutely like to improve the documentation of scikit-learn. We have employed one person for this. Hopefully we're going to get money to employ more people. First, it's a difficult thing because documentation is English. It's not code, and it's a different skill set. And it's really, about having people who are good at statistics and explaining them. Also, because scikit-learn is based by construction on consensus. Scikit-learn is not and will not ever be my view of how things should be done. So it's not about, doing a paper and saying, then I did a paper, this is the correct way of doing this, and then everybody should do it. It's about convincing other people. So it's kind of a boomerang effect. The research that I've shown here is research that we would like to come back in scikit-learn, but only because it has convinced people that it is good research. It's happening, but slowly. But yeah, I think it's important. And we have a MOOC, where the MOOC is slightly different. It's done by us, and here we try to distill a bit some good practice.
Cool, thank you.
Gael had a question.
Yeah, thank you, Gail, for this very nice talk. I have a naive question around the cross-validation. So if I have understood well, you advocate that it's good to do a cross-validation. But I also guess that it's you know how to do it when it's you have some specificity of the data, maybe when the data are IID. But in the real case, there is a question that how do you build the different folds? Should you go for as many folds as possible, or as many fold, a large number of folds, or on the reverse, to folds which have specific properties, and maybe the test that remains may be of different size for each time you run the fold. So then my question is that, is there a way or a theoretical way to, is it good also to optimize these cross-validation settings, or can you say a bit more about this cross-validation process?
Thank you, Gail, for the question. There are a few aspects to your question. One is, when do I stop? If I have infinite compute power, I can do many folds, but there's clearly, some form of diminishing returns. We do find that it's quite often useful to do 100 random splits. Now, what if my data are not IID? What if they have structure? I can't do random splits. I need to think a bit more about my splitting. I don't usually work with like structured data in the sense, for instance, of time series, but here you clearly need to account for, the contiguity of the time series, and there are ways of doing this. I'm not an expert, but I would say, you take patches. But there's also, this idea that the test set should always reflect the target population. And so we looked at that in this paper, which honestly isn't a great paper, but actually we have a more recent version of this. Same author, but a more recent version of this. But we did something that's fairly ugly, but it's based on rejection sampling, where you say, I want certain statistical property of my test set, and I'm going to reject until I get within error bounds. And you can do things to minimize, for instance, a confounding association. So the confounding association is a problem if it will not be reflected in your target population. If it's present in your study population, but not in your target population, because it's going to prevent, generalizing. So it's possible. I think there is probably a space for more research and more tools doing this. Thank you.
Thank you. Okay, one last question next to you. Yeah. No, you. Well, okay, anyway.
Hi. I'm thinking, could make sense to spend much more effort in improving benchmarks. I mean, of course, collecting data is not always possible, but being able to divide benchmarks into category, as you mentioned, okay, the oxygen measuring doesn't work on the skin. Can we differentiate between age, skin color in this case? The one is not racist thing at all. It's just, can we dig into category, try to have metrics, error rates specific for each one of these, and maybe next stage we try to collect a better benchmark, and that's on, and we go on this way. Because if you want to make a model working in production, you have to have an extensive benchmark that it's well representative. So does it make sense, something like this to you?
Well, I think we should be focusing much more on this than on developing new algorithms. I know this is not what people like to hear, but I think this is the bottleneck. And I think we should be focusing much more on acquiring new data, on characterizing this data, on understanding algorithms on this data. And it's becoming even more important in a world where these days we tend to reuse pre-trained model or pre-trained representation. And I really think that we should have tools that allow us to characterize better models, that we should have data sets, including our own data sets, that we understand, in which we understand the errors, and if there is structure in this error, and if there is structure in this error, it means there's this form of bias, it's not only variance. So basically understanding this, and to be honest, I think, sorry for the bad news, but I think that the craft of pure data scientist that is not tied to a specific application domain is going to die, or at least dwindle to a small number of people, and that we have a bubble here, and that in the midterm we're going to have people who understand machine learning but understand the kind of data they work with. I think that's where the scientific and application value is going to be.
Let's have just one last question.
I'm stealing all the time.
What's your opinion on reproducibility in the machine learning domain? I'm taking it's not very positive based on what you're talking about.
Well, I guess, I've had the chance to go through a bunch of different fields. Reproducibility suffers everywhere. It's a consequence of the incentives of the system. My take on the incentives of the system is very bad. I'm quite depressed by the incentives of the system. I also have the luxury of being a tenure and research director. So also one thing I'd like to say is that the young people tend to actually have higher standards than the old people. That's my experience. I don't like the term reproducibility, because reproducibility focuses on some form of like frozen food I can reproduce, which is important, but that's not all there is to it. There's a notion of generalizability, of reusability, of statistical validity, of more general validity, and that's what science is about. I think machine learning is suffering from its own popularity. Everybody wants to be doing it because, hey, it's exciting, and because it's good to have this on your CV. And we need to develop the right community standard where we're not building an ivory tower that makes it impossible for young people to join the field, but also where we're not lowering our standards. Difficult.
Okay, let's thank the speaker again.
Thank you very much, and thanks to the organizers.